So in the past, we've looked at a single proportion, and we've looked at two proportions, looking at the difference. Now, that works out fine if there's only two values on our explanatory and our response variables, but there could be many, many categories. And so just subtracting the two proportions doesn't work because there's several proportions to look at. So that's what we want to look at now, this idea of looking for differences when there's multiple proportions. And there's actually two ways of going about it. We'll look at both. And when we simulate, we'll use either statistic, and then we'll use one specifically when we use the theory-based approach. So here's some data here. We've got, this was from a study. They looked at 400 cars coming to a stop sign at this intersection. And they classified the car as approaching just as a single vehicle, not in any traffic, or multiple vehicles approaching the stop sign at the same time, and it's the lead vehicle. Or if it was multiple cars approaching at the same time, and it's a following vehicle. And so they wanted to look at, does that make a difference in the rate at which people actually come to a complete stop at the stop sign? So we've got complete stop or not, and then the three categories of how they arrived at the intersection. And there's the counts, and I even included the proportions there. So 151 cars here, but also 85.8%. OK, and then important here for us is that we know what in the population the rate of stopping or not stopping is regardless of category. OK. So if you recall, when we had two proportions, what we would do is look at just how the two deviated from one another. Was there a difference? And we could extend that idea to multiple categories. What we would need to do is look at, somehow add up all the differences. So we could look at the difference between single vehicle and lead vehicle, single vehicle and following vehicle, and lead vehicle and following vehicle. And that's one approach, and that's the book uses what's called the mean absolute difference. So we're going to look at those differences in absolute value. So we don't care whether it's positive or negative. So we'll take the difference in proportions, absolute value, absolute value, absolute value, and add those up. And then we'll average them. So, and we could either do this on the complete stop category or the not complete stop. Remember, those should come out the same either way because they're complements of one another. I'm just going to do it on the first category, complete stop. So this is what the book refers to as the mean absolute difference. Or MAD for short. So in our first category, we've got 85.8. The difference between the stop vehicle, or excuse me, single vehicle and lead vehicle would be the difference in absolute value, 85.8 minus 90.5. And then we would add to that, oops, on top of my chart here. The book refers to this as MAD. So we would add to that, let's just stack these. We'll add to that. We could do single vehicle minus following vehicle. So 85.8 minus 77.6 in absolute value, and then add the difference between, the only thing left is lead vehicle compared to following, so 90.5 minus 77.6. So we've done all possible pairings. This could be quite a lot. If there's more, the more categories you have, the more pairings to make sure you pair them all up. In this case, we've only got 3. So we would total those up, which that comes to, actually, I don't know what that comes to. We would take that total. I didn't compute the individual total. Whatever that sum is divided by 3. And that comes out to be 8.6%. Or I'm going to write it as a decimal 0.086. So all of these will be positive numbers. That's what the absolute value achieves, or possibly 0, I guess. And then add those up. And since there's 3 differences here, we divide by 3 to get the average or mean absolute difference. OK, so we could use this as a statistic. This is our measure of how much these things are deviating from one another. That's one way to measure it. Another way to measure it would be, remember we talked about how you could figure out what these categories should be ideally if there was no association. So if there was no connection between the approaching the intersection, what type of approach, and whether you stop or not, you would expect these percentages to be the overall percentages. So 85.3 and 14.7. You would expect those percentages in every category, with some slight deviation, obviously, because of just sample variation. But we could figure out what those ideal values are and see how much we differ from those. And that is the second type of statistic we could calculate. This is called a chi-square because it's the distribution that this generates is called a chi-squared distribution. So this chi-squared statistic, let me see right here. That's a Greek letter chi squared. That square just has something to do with how the distribution is computed. What we do is we sum up all of our observed values, so the actual counts, how much they differ from the expected value, square that over the expected value. So we're going to go through and do that for all the categories. So first of all, you would have to figure out your expected values. Well, you know, for example, you want these to come out to be these percentages. So in this first category right here, I would like this to be, the total here was 176, right? I would like to know what 85.3% of 176 is. And if I round that, it comes out to be 150. So to get that percentage to be what the population percentage is, it'd have to be 150. And then just subtracting, we get that that one should be 26. Again, this category right here should be 85.3% of the 126 right there, which comes out to be 107. And then just by subtracting, we get that the other one is 19. And again, this one we'd like to also be 85.3% of its total, 98, which comes out to be 84. Now, I rounded all these to the nearest integer just to make this easy for us to write and talk about. But typically, you wouldn't round them, even though it doesn't make sense to have 150.3 cars. In computing this chi-squared statistic, you would just leave those unrounded. OK, so what ends up getting calculated here? So this is the difference between what we observed and what we expected. So in this first category, we observed 151, and we expected 150. So a difference of 1 squared over what we expected. So it's the difference as a out of the expected, weighted by the expected. Next, we had 114. We expected 107 squared over what we expected. Next, we had 76. We expected 84 squared over the expected. And we do this for all 6. which is a little bit different than this, right? Because this was operating off those proportions, they're really kind of independent of counts. And these were just complements. We just do the single category. But for the chi-squared, you do this for every cell in the table. So next, we observed 25. We expected 26. And this difference should be the same as that difference since there's only two categories. But it's out of the expected, which is 26, not 150 this time. Next, the expected was 19, and we observed 12. And then lastly, we expected 14, we observed 22 out of 14. So you would, whoops, not equals, plus that. So you'd add up those 6 terms. In this case, it came out to be about 8.4. So 2 different styles of statistic. This mean absolute difference, which works great for simulation. There's some reasons on the theory end why the chi-squared is a better statistic to use, because it's got a nice distribution to it that we can describe mathematically. But when we do our example of simulating, we'll look at both of these statistics. When it comes to the theory-based approach, it'll be the chi-squared statistic. So next, we'll look at what happens when we try and establish, is this significant, right? We've somehow measured how these proportions deviate from what we would expect if there was no connection in the variables, or this chi-squared statistic. So we've got a statistic, one or the other. Now we need to test, is that significant? Are we seeing evidence of a connection between the two variables, between how you arrive at the intersection and the likelihood of actually coming to a complete stop? So we will look at that simulation next.